Okay, so if you look in the text, 6.1 is confidence intervals for population mean when sigma is known. I typically don't do that section because it's not practical. In practice, we do not know sigma for the most part. Sigma is the population standard deviation. We always rely on the sample to give us the standard deviation. So 6.2 is more important in practice than 6.1. It's a rare case. The notation for population mean is mu. We've seen this a long time ago. So have a fancy term, point estimate. Point estimate is nothing but a statistic. You know, we have the population parameter and we use the sample to come up with an estimate of that parameter. We call that statistic. I'm introducing a specific phrase, point estimate. There is a reason. If mu is the population parameter and I want to estimate it using a sample, what notation do we usually use for the sample mean?
X bar.
X bar. Very good. So X bar is simply the sample mean. We also denote it by the letter mu hat. Mu hat is more formal than X bar, but I believe your textbook uses X bar. So we are going to make use of the sample mean to infer something about the population. Let's say the population mean of interest is the average amount an FTC student spends on coffee per week. But let's say I collected a sample and the sample gave me an answer of $22.87 per week. So I used some sample, I got this average to be 22.87. That average is what we call a point estimate because it is a single point, right? So X bar is nothing but point estimator or point estimate. Here is a question. If I went and collected a different sample, do you believe I'll get the same average? No, right? It is not realistic to expect that. It will definitely change. But if the truth is going to be around this value, I can form an interval to say that if I go and collect different samples, it is likely to fall between two numbers. And I could say perhaps 20.87 and 24.87. Good. So a point estimate is a single point, and an interval estimate is from $20.87 all the way up to $24.87. And let's say I have 95% confidence. I'm being more confident with this interval than a single value. Do you agree? Now, would you bet on that single value? No, right? If someone came up to you and asked you, well, what is the average amount spent on grocery per week by a student? You say it's $22.87 based on a sample that you collected. And the person or people ask you, well, are you 100% certain? Would you bet your life on this? Would you? I wouldn't. Because if they went and collected a different sample, this is going to change. But if I have an interval of this sort, I could simply say, well, about 95% confident if you went and collected another sample, it is going to fall between those two values. Okay. Now, which is more beneficial to us? The interval, correct? Because we're giving a range of values that are possible for, or that is possible for me. Good. So our objective is to find that range. Now, range is nothing but an interval. Do we agree? The lower endpoint of the interval, upper endpoint of the interval, which is why we call this a confidence interval. Would you want to have an interval with 20% confidence? That's the answer, right? What would you want to say something with only 20% confidence? We typically want that number to be bigger than 90. So the usual values are 90%, 95, and 99. The calculator calls it a C level. I don't know what book uses, but the common values are 0.90, 0.95, 0.99. The amount of confidence that you would have is just in terms of a percent. You have 90%, 95%, and 99%. Good. Now, if you start here, you have to have some sort of a reason, or you need to justify as to how you went there and there, correct? I can't arbitrarily make stuff up on either side. There has to be a reason that I say, okay, it is going to lie between 20.87 and 24.87. That is our objective, to get to that rationale. So we find something called E, uppercase E. Uppercase E is simply the margin of error. So we're going to add and subtract the margin of error from the point estimate to get that interval. The margin of error is always a product of two things. Positive critical value multiplied by the standard error. Good. This is just the formula. So going to put a notation here from this card. So T subscript 1 minus alpha over 2, comma, n minus 1, multiplied by s divided by square root of n. That formula is not going to change. That is the formula for margin of error if you're trying to find the confidence interval for population mean when you do not know the signal. So once we have the margin of error, I'm leaving this here for a reason. Once I have the margin of error, CI stands for confidence interval. Leave some space there. Going to start in the middle, which is the point estimate. I'm going to add margin of error, subtract margin of error. I'm going to say that the population mean is likely to lie between those two lines. Does that make sense? In my example, I'm going to argue that the average amount spent on Coca-Cola by a student is between 20.87 and 24.87. Just by looking at it, can you tell me what E is in my example? 2. 2, very good. So if I add 2 to 28.87, I get 24.87. Subtract 2, I get 20.87. So our goal is to find the margin of error. The sample is going to give us the sample mean. And there is this funky notation, alpha. Think of goldfish. Right? Alpha stands for significance level. Significance level is always 1 minus the level of confidence or the confidence level. So 1 minus 0.9 is 0.1. 1 minus 0.95 is 0.05. 1 minus 0.99 is 0.01. You may say, well, why is it bringing up alpha? Brought up alpha because alpha plays a role in coming up with this critical value, and alpha is the number that is going to determine the confidence in your interval. Does that make sense? Because alpha is related to sea level, that is related to the amount of confidence. So alpha is going to determine how confident you will be when you find that interval. Does that make sense? Okay, so that is easy to find. S is the standard deviation. N is the sample size. We know how to use one variable statistics in the calculator, but in the sample, it is going to give us the mean, the standard deviation, the sample size, all of that stuff. I can get it easily. But got to find the critical value. Section 5.3. That breaks this part. What did we do in 5.3? Mind you, the exam's on Wednesday. Very good. 5.3 is inverse norm. So what do we find anytime we use inverse norm? Do we find the area?
The sectional area.
Sectional area.
Okay. The z-score, the z-score.
We tried to find the z-score. If you recall, I believe it was problem 21. I forget. But we had area in the middle, right? 47.5%, 47.5%, in total 95%, and 0 lies in the middle. And we did z equals question mark, yes. So that is simply a z-score. And I drew a chart at the very beginning of class last time when we did 5.3. And I said, as long as you have this chart, you can pretty much guess your answers on an exam. And I said it is possible because z-scores are related to something. I'll give you a hint. Starts with the letter P, and it is a type of fluorine. Percentile. Oh. So percentiles. So each of these values are nothing but percentiles. So put that picture in your cheat sheet so you can guess properly. Process of elimination. So we are going to find the percentile. So with a bell curve, that percentile on the right is the positive critical value. The percentile on the left is the negative critical value. But me so far. So whatever you found in 5.3, we trained you to, do all those problems because you can use them here. So anytime you found that z-score on the right, you pretty much sort of found a critical value in relation to this particular topic. And left-hand side, you found the negative critical value. But if you notice, I didn't use the letter Z. I rather used T. So no difference at all in terms of the process in finding the percentiles. The only difference, which you can't see, that looks like a bell curve, Watson, right? Correct. But it's a T distribution, hence the letter T. Good. So you may not be able to notice the difference between a bell curve and a T distribution. In terms of shape, both look very similar. But in terms of the numbers in the formula, T distribution is different from a standard normal distribution. Good. So I'm just going to take the same notation and transfer it over here. 0 is in the middle. That there is a T on the right. There is a T on the left. Good. 95% is in the middle, correct? So that corresponds to the amount of confidence. So if I picked an arbitrary alpha, I can call the amount of confidence in the middle as 100 times 1 minus alpha. You can use your calculator to plug values in. If you plug in 0.05, what is 1 minus 0.05? 0.95. If you multiply by 100, what do you get? 95%. If I change that alpha to 0.1, 1 minus 0.1, 0.9, 0.9 times 100, that would become 90%. Does that make sense? So this number is that number over there. The reason why I'm using 1 minus alpha over 2 is because of the shaded areas. In total, we know the area under the curve is 1. Okay? And if 1 minus alpha is in the middle, what percent is on either side? Difficult to see. How about this? 95% corresponds to an alpha of what value? 0.05. This is the 0.05 case. If 95% is in the middle, what percent lies on each tail? 2.5%. Which is 0.025, correct? What is the area over there? Same. So if alpha is 0.005, the area in each tail is half of that value, correct? So in terms of alpha, how can I write that 0.025? So alpha is 0.05, and that area is half of 0.05. So in terms of alpha, how can I write that? Thank you, Hannah. Alpha divided by 2. Right? Same over here. Alpha divided by 2. Good. The notation over here is alpha over 2, comma, n minus 1. Over there is 1 minus alpha over 2. Because the area on that tail is alpha over 2. Can someone tell me as to why I wrote it as 1 minus alpha over 2 and alpha over 2 here? Okay.
It all adds up to the point that you need to take away the alpha on the side, essentially.
So all I'm doing is I'm taking away the alpha over 2 from what? Yes. In other words, I'm looking for the area below that number. Agreed. So that is nothing but a percentile. So that t-score is a percentile. The fancy name that we use is the positive critical value. Good. Over here, the area below that value is alpha over 2. Hence, I write it as t sub alpha over 2, comma, n minus 1. Good. How do we find this? Pick up your calculator. If you have the newer version or TI-84, relatively new, or TI-83 plus, you should see inverse T in the same location where we get normal CDF from, or inverse norm. So second class. Do we see inverse T? You simply put the area below, followed by n minus 1. The only difference between inverse norm and inverse T is that inverse T will require that n minus 1. Good. Likewise, on this side, take a guess as to what you would enter.
1 minus
Minus what, Nick?
alpha over 2.
Comma, n minus 1. Good. Do you have to find both of them?
Yes.
Is it necessary? Or could I find one and use that to find the other?
You could find what you said.
I could find one and use that value to find the other. So if this value is negative 1.95, that would be positive 1.95. Does that make sense? Okay, so we use the t distribution and inverse t to find the positive critical value. Finding the standard error is easy. It's simply the sample standard deviation divided by the square root of sample size. Good. I'll get in this formula. I'll get the margin of error. Take that margin of error, add it to the point estimate, sample mean, you'll get the upper endpoint. Subtract it from the sample mean, you'll get the lower endpoint. Yes.
What if you don't have the inverse?
1 second. So if you don't have the table, excuse me, if you don't have inverse T, you would use the table. It's giving you options, confidence interval, and these, this is chapter 8. We'll talk about that later. So you have 3 rows on the top, right? And the first one says level of confidence, yes? So it's giving you 0.8, 0.9, 0.95, 0.98, and 0.99. So suppose we are doing 95% confidence. Which column should you pick? Matthew. The third column, because from the first line it says 0.95, which is 95%. So I'll pick the third column, and here the header is d.f, that stands for degrees of freedom. This number, n minus 1, is called the degrees of freedom. So you can write that. So df is n minus 1. And df stands for degrees of freedom. I won't get into that. If you're interested, come and talk to me. Let's say the sample size, give me a number between 10 and 30.
21.
21. If the sample size is 21, the degrees of freedom is always 1 less. So 21 minus 1 is 20. The confidence level is 0.95, so 20. Third column, the value is 2.086. Good? So the critical value, the positive critical value that you would use in finding the interval is 2.086. Good. with me. Let's see if we get the same answer with the calculator. Casey? Okay. Using using the table, and I used a confidence level of 95%. And we picked the third column and sample size of 21. So degrees of freedom is 20. I got 2.086. In the graph here, 95% is in the middle. So what is or what percent lies on the left hand? 2.5% or 0.025. So the area below the left critical value is 0.025. So in your calculator, second part, option number 4, I'm going to find the left critical value, multiply by -1 to get the right critical value, which is the positive critical value. So in Mercy, the area below is 0.025. The degrees of freedom is 21 minus 1, which is 20. Good. Yes. Enter. Negative 2.0859. Rounded to 3 decimal places, you'd have negative 2.086. On the left-hand side, it is negative. You multiply by -1, you will get the right-hand side critical value. Good. So you can either use the table or you could use inverse T. Yes.
No, never mind.
Okay.
Sorry, I figured it out.
Are we clear?